So as you can see for text, there is this confusion of what method to use. Should we use recurrent neural networks? Should we use recursive neural networks? Or should we use convolutions? Or should we use attention? So I'm going to introduce all of them because it's going to help you decide the pros and cons of each one. Convolutions are mostly for images, and we're going to do some images later on in this course as well, when we are going to do multimodal learning and generative adversarial neural networks. We're going to deal with images, so it's a good time to learn about convolutions. But these are convolutions for sentences, and sentences are one-dimensional. So what are we going to do? We know that each word in a sentence is a vector. So that's by default. That's what we are going to do by default. That's how you represented words in a sentence. These are vectors, and each sentence is a sequence of length n. So you're going to have x1, x2 up until xn. This is your sentence. And each one of these x1, x2 up until xn are k-dimensional vectors. You can think of that as a one-dimensional image. So for images, you have 2 pixels, 2 dimensions for your pixels, the x-coordinate and the y-coordinate. Now this is just the x-coordinate or the y-coordinate for an image. Now you can have a filter, and the filter size is going to be h. So this is how many words per each convolution operation you're going to end up using. And each one of those, because you want to take that filter and multiply it by a vector, has to be a matrix. Okay, so each one of these W's, W1, W2 until WH, are matrices. And these are taking you from dimension K to dimension M. And K could be either the dimension of your word vector representation, which was 256 or 1024, or it could be a one-hot vector for the entire size of your vocabulary. So you have the freedom to choose whatever that you want. So we are going to deal with the first layer of a convolution. We learned how to represent words. Now we are going to introduce convolutions, and we are going to introduce what is Wj and what is B. This is your kernel, this is your filter, this is the number of features that you're going to end up with after applying your filter, and B is a bias. It's going to become clear. So what are we going to do? We're going to take a window of size h from this input sequence. So let's say you pick x1, x2, and x3, and let's say h is 3. So you pick x1, x2, x3, and you're going to multiply that by w1, w2, and w3. So it's going to be w1, x1, w2, x2, w3, x3, and then you just add them up. This is going to be a m-dimensional vector, the output after this summation. You're going to add a bias to it to take care of shifts in your mean distribution, the mean of your distribution. So the bias is going to take care of that. Then you're going to introduce a nonlinearity like tan H or ReLU, and that's going to give you your first entry of your next sequence. So a sequence goes in, a sequence goes out. So this is going to give you C1. Then for C2, what are you going to do? You're going to take X2, X3, and X4, and then do the same thing here. For C3, you're going to take X3, X4, X5, and then you go up until the end. And you are right if you are thinking that you're going to have less numbers after these operations. And yes, you're right. So if the length of your original sequence is n, the length of the sequence C is going to be less than that. Okay? So a sequence goes in, a sequence goes out. And a sequence of k-dimensional vectors goes in, a sequence of m-dimensional vectors comes out. But in the end, we are interested in a single vector. You don't want to end up with a sequence. You want to end up with a vector so that you can use that for classification. It's exactly what we also did in recursive neural networks. So that's what we are going to do. And these are pointwise operations again. Okay, by default, it is going to be pointwise. You take the first entry of this m-dimensional vector for every single vectors in your sequence, and then you find the maximum, and you put it in Z, the first entry of Z. The second entry of Z is doing a maximum over n minus h plus 1 numbers, and then it's going to give you a vector in the end. So you can think of this as max pooling. It's global max pooling. Now, Z is going to be m-dimensional. We don't like m-dimensional stuff We like 5-dimensional stuff because in the end, our classification task is a 5-dimensional task. It's classifying between 5 entries. So again, you're going to multiply that by a matrix to do the projection for you from m dimension to 5 dimension. So far, so good. Are there any questions?
Would we often do the convolution multiple times before the max pooling, just like with images?
You could do it. Yes, absolutely.
So in this example, we're just doing one convolution, one max pooling, and then a prediction at the end. But you could layer it up deeply.
Exactly.
Okay.
But
exactly.
if we have a sentence, it's likely that we can't sort of reduce as much because there might be only like 3 or I don't know 5 words in the sentence. So you can only apply so many convolutions before you just.
Yes, exactly. So what you're saying is that the size of n matters, and you're right. There are only so many convolutions that you can do, but a couple of them should be fine. And what is the difference between this method and the previous method that we just saw, recursive neural networks? For this one, you don't need to have a tree structure. So the previous one depended on a tree structure and then classifying each node properly. So you needed to do some pre-processing on your data. This one doesn't need any pre-processing on the data, okay? And then when you go from one sequence to the next sequence, it's as if you're going from your original sentence to one layer up in your tree. So you're now combining words together. Another analogy between images and sentences is that these are your coordinates. Let's say this is your x dimension for your images. But then if you remember, for images, you had k to be 3, red, green, blue. Now you have a word vector representation. So k could be 100. So these are the number of channels. So this is another analogy for those of you who know convolutions. So there is a question, is this also that this method deals with several words in comparison to the tree that deals with 2 at a time? Yes, exactly. If you set your age to be 2, then you're going to process 2 words at a time. If you set age to be 3, you're going to process 3 words at a time, or 5 words at a time. So you have a choice of age that you make. Does that answer your question?
Yeah, it just sounds like this method will have a better, I guess, measurement of the words in comparison to just 2 words at a time in comparison to like many.
Probably. And we're going to see the performance metrics later on. But for now, there is also another technique in machine learning that we use a lot. In deep learning, the reason that deep learning succeeds is not one of the main reasons, or a couple of the main reasons, are these nonlinearities and the particular choice that you make for those nonlinearities. So the paper rectified linear units was really influential. And the other one is doing dropout. And what is dropout? You want to, these Z's that you're seeing, they are neurons in your neural network. So you're gonna have M neurons, 1, 2, up until M. What you want to do for your dropout to achieve is that these neurons need to operate independently. So for instance, if I give you an assignment, I want you guys to be able to carry out that assignment individually. If you're in a group, I don't want you to always rely on your group mate. So I don't want the entry Z1 to always rely on entry Z10. That's why you're introducing a bunch of randomness in your neural network during training. And what is R? With probability P, you're gonna drop a neuron. So you're gonna multiply that by a 0. So you're dropping it. And with probability 1 minus P, you're keeping that neuron. Okay, so with probability P, you're dropping it. With probability 1 minus P, you're keeping it. And that's gonna give you the dropout algorithm. And this is gonna happen per each data point that goes in. You're gonna drop a neuron. But in the end, you want to come up with an algorithm that is deterministic. So you don't want your predictions to be stochastic. How are you gonna do it? You're gonna average out the predictions of all of these models that you're gonna end up with. So per each R, you're gonna have a different model. How are you gonna average it out? You just downweight your original weight by the probability that you used to drop your neurons. Okay, this is gonna help your algorithm train much better and generalize much better. So this is another technique that I want you guys to learn. you're gonna hear about Dropout a lot. So this is a 3-line introduction to Dropout. Okay, any questions? I think we are over time. For those of you who want to leave, you can leave. And for those of you who want to stay and ask questions, I'll be around.
Yeah, I have a question about the dropout. So I get the dropout. So for every neuron, we have this probability of dropping it out in the forward pass. I didn't quite catch the last part of averaging the results.
So yes, you have two options. Once you're doing your training, there is some randomness. Each time that the data entry goes in, you're gonna sample from this distribution, and then you're gonna drop that entry. But then in the end, when you want to take your deep neural network to production, you don't want things to be random. You don't want your classifier that is doing your sentiment analysis to give you random predictions each time that the data set goes in. So how can we deal with that? One option is to, whenever a data goes in, you can make multiple samples from this distribution and then average out the predictions. That's one option. But then what is the problem with that? Can you tell?
Still not deterministic.
It is going to be very close to deterministic. So you're doing a Monte Carlo averaging.
Yeah, but it's not going to be the same every time, which is what you want from your prediction software.
Yes, but it's going to be very close. But
it'll be more expensive. Like why?
It's going to be, yes. So it's going to be more expensive.
Yeah.
So yeah, during testing, during production time, you want things to be extremely fast. So you don't want to do Monte Carlo. You want to avoid it. So what are we going to do? Rather than averaging it out, doing Monte Carlo, we are going to do an estimate. Because this is a binomial distribution, you can have an estimate for the average weights. And the way that you're going to do it is you have your original WY, which is being trained through Dropout and your training process. But then you're gonna, when you want to take it to production, you just downweight it. So in production, what are you gonna give to your customer, or what are you gonna employ? You're gonna give to your customer these word vector representations. You have to give them that. You have to give them these W's and B's for them to be able to run your model. And at the same time, you have to give them P. What P did you use? And once they know that, they're going to multiply WY by P. It's going to give them a new W, and that W is going to go into production. That's going to go here. I hope that answers your question. And
yeah,
the rest, you can.
Oh, yeah.
I have another question related to Dropout, because I know one of the reasons why when neural nets are being popularized, they're using the sigmoid functions because it's smooth. And you don't have smoothness for ReLU or for ReLU functions, it's still piecewise linear. But with the Dropout, that seems like you might have a lot of issues with training because you're not really having these smooth functions for stuff. Is that like, how's that really handled?
So why do we use Dropout? We use Dropout because if you report your performance metrics on your training data, nobody is going to care. So if your loss function is going down amazingly fast and to very low levels, nobody is going to care. What people are going to care about is the performance of your method on your test data. So Dropout is going to help your method regularize. It's going to help it not overfit to your training data. And then it's going to give you better performance on your test data.
I guess my question is more of like more when you actually implement it, because the reason why you like having a smooth function is because then you have for the back propagation portion of the network training, it's really easy to compute the partial derivatives there. But with the Dropout, how's that impact the ease of doing the back propagation?
Still the same thing. So in your back propagation, whenever a node is absent, the gradients of that node are going to be 0.
Okay.
So everything is going to be fine.
Okay, yeah, that makes sense.
Okay.
And then with the discontinuity, I don't think it's an issue because it's like impossibly unlikely to get an input which is right at the cusp where you'd have any ambiguity about derivatives.
Yes, and the way to think about ReLU, and the way that I like to think about it, is that it is positive in the positive regimes, and then it's 0. But then each data point that goes in, it's either going to end up on the 0 side of your ReLU, or it's going to end up on the positive side of your ReLU. And if it ends up on the positive side of the ReLU, then these weights and biases of your neural network are going to get updated.
Okay. Thanks.
And for many of your examples, you're going to end up on the positive side. And it means that your weights and biases are going to get updated through backpropagation and stochastic gradient descent.
Thanks.
Yeah.
Is there a way to, I'm just familiar with Dropout, that you're only doing Dropout during training. That's why I'm a bit confused about why do we have to multiply P by W? Can't we just not use W during testing?
So W is the one that is memorizing your data. It's going to help you classify your, it's going to help you solve your problem. So you're going to need to carry W with you. But then if you use W, the problem is it's going to be overestimating the probabilities that are going to come out of your method. So it's going to be an overestimation because WY is true for the cases when you're not dropping. But then most of the times you're dropping. Actually, P ratio of the times you're dropping that neuron. That's why you have to downweight that. Because in the end, you want to take an expectation. You want your algorithm to be able to have a good performance on average. Okay?
Okay, yeah, that makes sense with the overestimating, because we're dropping the neurons, so the ones that are not being dropped are going to compensate for the ones that dropped. So overall, we're going to have a model that overcompensate because we always drop something.
Exactly. So that's why you have to multiply it by P. And that's actually going to end up being an estimate of the expected value. It's going to be an estimate to that Monte Carlo approach that I just explained. Okay. Any other questions?
Yeah, like if you used P equals 0.5, then all your neurons in training would learn to become twice as strong. And then if you turned them all on at the end, you're gonna have double the activation that you want.
Yes, that's a perfect way to put it. Yeah.
And so you cut it in half and it's back to what you want.
Yeah, so that's intuitively why this is working, and mathematically it's an estimate for that Monte Carlo averaging.
Would it make sense during training to do to change P by dynamically? Like, so like say you start at 1 and then slowly decrease that to 0.5 and let your training finish there? Would there be any reason to do that?
Yes, so you can actually do that. So all of these all of these ideas that you're coming up with, these are practical ideas that are going to help you. So yes, you're right. Maybe initially you want your network to train faster, so you're going to have a schedule for your P. But you need to study that, whether that's going to actually end up giving you the best performance in the end.
With the intuition there being that not dropping out is going to speed training, but then later on it's going to overfit. So you want to dial up the dropout as you get closer to overfitting?
Yes.
Okay.
Wouldn't dropping out actually speed training because you have less parameters to work with?
You have, with dropout, you still have the same number of parameters.
You don't have to update all of them because some of them are being dropped out.
Yes, so you don't have to update them. So what they are saying is that if you have a more powerful model and more parameters, then you're going to be able to overfit your data faster. And in the end, you can set P to be lower because you don't want them to be dependent on each other. So that's an idea to be tested. It's a good idea. But...
Okay, that makes sense. Thanks a lot.
And don't worry about the number of parameters in neural networks, because in one single pass of backpropagation, you're going to get the derivative with respect to all of your parameters in one pass. It's the same cost. Okay. Any other questions?
Thank you.
Yep.
Just to be clear, this is more on the last slide, but when we're talking about like just the dense vector representations of the words, I guess it could matter to some extent, but it doesn't really matter whether we use like embeddings created with glove or created through word2vec, right? Any of those embeddings will be valid for these models.
Yes, so any of them would be valid. Why? Because you have an independent training process going on here. Even if you initialize them random, given enough data, you're going to be able to learn L.
Okay.
So you can use word2vec or glove to initialize this and then do the training.
Gotcha. Thanks.
Yeah. Any other questions?
No, thanks. Bye.
Okay. See you next time.